Hello, welcome students. I am Rekha Thorat, Associate Professor. Today we will see next part of indeterminate forms. First we consider indeterminate form infinity upon infinity. Let limit of fx as x tends to a equal to infinity equal to limit of gx as x tends to a. That means both of the functions fx and gx have limit infinity as x tends to a. Then limit of fx upon gx as x tends to a takes the indeterminate form infinity upon infinity. In this case also we show that limit of fx upon gx as x tends to a equal to limit of f dash x upon g dash x as x tends to a. Let limit of fx upon gx as x tends to a equal to L, which is finite and non-zero. Also, limit of 1 upon fx as x tends to a equal to 0 equal to limit of 1 upon gx as x tends to a. Since limit of fx as x tends to a equal to infinity, limit of 1 upon fx as x tends to a equal to 0, since 1 upon infinity is 0. Also, limit of gx as x tends to a equal to infinity. Hence, limit of 1 upon gx as x tends to a equal to 1 upon infinity equal to 0. Then, L equal to limit of fx upon gx as x tends to a equal to limit, that means limit of fx upon gx as x tends to a can be written as limit of 1 upon gx divided by 1 upon fx as x tends to a. That means after simplification it is of the form limit of fx upon gx as x tends to a. Why we written this form of 1 upon gx upon 1 upon fx? Since limit of fx as x tends to a equal to infinity and limit of gx as x tends to a equal to also infinity. To convert this form infinity by infinity into 0 by 0 form, we take limit of 1 upon gx divided by 1 upon fx as x tends to a. So that 1 upon infinity means 0 and 1 upon infinity is also 0. So that we get form 0 by 0. So that using L'Hopital's rule, that is L'Hopital's rule, if the indeterminate form is 0 by 0, then we take derivative of numerator and also derivative of denominator. So we get L equal to limit of derivative of 1 upon gx. Derivative of 1 upon gx is minus 1 upon gx bracket square, and derivative of gx is g dash x, divided by derivative of 1 upon fx is minus 1 upon fx bracket square into derivative of fx is f dash x. That means we have taken derivative of numerator and derivative of denominator of above step, since the form is 0 by 0 by L'Hopital's rule. Hence, L equal to limit x tends to a. After simplifying, we get L equal to limit x tends to a in bracket fx upon gx bracket square into g dash x upon f dash x. That means after simplifying, we get L equal to limit x tends to a in bracket fx upon gx bracket square into g dash x upon f dash x, which is equal to limit x tends to a in bracket fx upon gx bracket square into limit of g dash x upon f dash x as x tends to a. But we have fx upon gx, limit of fx upon gx equal to L. Hence, LHS side is L equal to RHS side is L square into limit x tends to a g dash x upon f dash x, from which after simplifying we get L cancels, so that we get limit of f dash x upon g dash x as x tends to a equal to L. That means we have taken the step limit of g dash x upon f dash x as x tends to a in LHS side, so that finally we get limit of f dash x upon g dash x as x tends to a equal to L. Thus, limit of fx upon gx as x tends to a equal to limit of f dash x upon g dash x as x tends to a. That means same result is obtained when the indeterminate form is infinity by infinity. That means when for solving examples, when the form indeterminate form is infinity by infinity, we have to convert this form into 0 by 0 by taking reciprocals of the functions and obtain the result. That means finally we get result limit of fx upon gx as x tends to a equal to limit of f dash x upon g dash x as x tends to a. That means first convert the indeterminate form infinity by infinity into 0 by 0 form, and then by using L'Hospital's rule we take derivative of numerator and denominator and take the limit of the function. Thus, we get limit of fx upon gx as x tends to a equal to limit of f dash x upon g dash x as x tends to a for the indeterminate form infinity by infinity. Now, we consider the working rule. Number 1 is, in both the indeterminate forms 0 by 0 and infinity by infinity, to obtain limit of fx upon gx as x tends to a, differentiate numerator and denominator separately and then put x equal to a. If indeterminate form is again obtained, apply the rule again and again and follow the same till the limit is obtained. That means if the indeterminate form is 0 by 0 and infinity by infinity, we differentiate limit of fx upon gx as x tends to a. That means we differentiate numerator and denominator separately and then put x equal to a. If we get again indeterminate form 0 by 0, then same step is repeated and till the limit is obtained. If the determinate form is infinity by infinity, also we get the same results, so that in this case also we differentiate numerator and denominator separately and then put x equal to a. If indeterminate form is again indeterminate for infinity by infinity is obtained, then we apply same rule till the limit is obtained. Now we consider some results, important limits. First result is, you know these results, limit of sin x upon x as x tends to 0 equal to 1. Second result is limit of tan x upon x as x tends to 0 equal to 1. Third result is limit of sin inverse x upon x as x tends to 0 equal to 1. Fourth result is limit of in bracket 1 plus x bracket raised to 1 upon x as x tends to 0 equal to e. Fifth result is limit of a raised to x minus 1 upon x as x tends to 0 equal to log of a. Sixth result is limit of e raised to x minus 1 upon x as x tends to 0 equal to 1. Also consider the results. Sin hyperbolic x, you know that sin hyperbolic x equal to e raised to x minus e raised to minus x upon 2. Also sin hyperbolic inverse x equal to log into bracket x plus square root of x square plus 1 bracket complete. Similarly, you know that cos hyperbolic x equal to e raised to x plus e raised to minus x upon 2, and cos hyperbolic inverse x equal to log of in bracket x plus square root of x square minus 1 bracket complete. Also you know that tan hyperbolic x equal to e raised to x minus e raised to minus x upon e raised to x plus e raised to minus x, and tan hyperbolic inverse x equal to 1/2 log of in bracket 1 plus x upon 1 minus x bracket complete. Now consider some useful series expansions. E raised to x equal to, first expansion is e raised to x. E raised to x equal to 1 plus x square upon 2 factorial plus x cube upon 3 factorial plus dash dash dash. Second expansion is of sin x. Sin x equal to x minus x cube upon 3 factorial plus x raised to 5 upon 5 factorial minus x raised to 7 upon 7 factorial plus dash dash dash. That means alternate plus and minus sign. Then third expansion is of cos x. Cos x equal to 1 minus x square upon 2 factorial plus x raised to 4 upon 4 factorial minus x raised to 6 upon 6 factorial plus dash dash dash. Here also alternate plus minus sign is present. Fourth result is of, fourth expansion is of tan x. Tan x equal to x plus x cube upon 3 plus 2 upon 15 x raised to 5 plus dash dash dash. And fifth expansion is sin hyperbolic x equal to x sin hyperbolic x is equal to x plus x cube upon 3 factorial plus x raised to 5 upon 5 factorial plus x raised to 7 upon 7 factorial. That means expansion of sin x and sin hyperbolic x, these are different. That means in expansion of sin x there is alternate plus minus sign, but in expansion of sin hyperbolic x all the terms are positive. Sixth result is expansion of cos hyperbolic x. Cos hyperbolic x equal to 1 plus x square upon 2 factorial plus x raised to 4 upon 4 factorial plus x raised to 6 upon 6 factorial plus dash dash dash. That means in expansion of cos hyperbolic x all the terms are positive. Seventh expansion is of tan hyperbolic x. Tan hyperbolic x equal to x minus x cube by 3 plus 2 upon 15 x raised to 5 minus dash dash dash. That means alternate plus minus sign is there in the expansion. Eighth result is log of 1 plus x. Log of 1 plus x equal to x minus x square upon 2 plus x cube upon 3 minus x raised to 4 upon 4 plus x raised to 5 upon 5 minus dash dash dash. Alternate plus minus sign is there in the expansion on RHS side. Ninth result is of 1 plus x raised to m. equal to 1 plus x raised to m equal to 1 plus mx plus m into bracket m minus 1 upon 2 factorial x square into x square plus m into bracket m minus 1 into m minus 2 upon 3 factorial into x cube plus dash dash dash. Now we consider some examples. Consider first example. Evaluate limit of 3 raised to x minus 2 raised to x upon x as x tends to 0. To solve this example, first see which of the indeterminate form is there. First take limit of given function as x tends to 0. 3 raised to 0, anything raised to 0 is 1. So 3 raised to x as x tends to 0 is 0. Also limit of 2 raised to x as x tends to 0 is 0. That means 0 minus 0, that is 0 in the numerator. And in the denominator x means 0, that is indeterminate form is 0 by 0. So that limit of 3 raised to x minus 2 raised to x upon x as x tends to 0 is here denominator form is 0 by 0. So we use L'Hospital's rule. That means we take derivative of numerator and denominator separately, so that we get limit of 3 raised to x minus 2 raised to x upon x as x tends to 0 equal to limit x tends to 0 derivative of numerator, that is derivative of 3 raised to x is 3 raised to x into log of 3 minus derivative of 2 raised to x is 2 raised to x log of 2 upon in the derivative of x is 1 in the denominator. Here we use the rule that derivative of a raised to x is a raised to x into log of a. Finally we get limit of 3 raised to x minus 2 raised to x upon x as x tends to 0 equal to log of 3 minus log of 2. Since 3 raised to 0 is 1 and 2 raised to 0 is also 1. So we get the result as limit of 3 raised to x minus 2 raised to x upon x as x tends to 0 equal to log of 3 by 2. Now consider second example. Evaluate limit of x minus sin x upon x cube as x tends to 0. As x tends to 0, in the denominator put x equal to 0, so that we get 0 minus sin of 0 is also 0. And in the denominator x cube means 0, so that we get in the indeterminate form 0 by 0. So we use L'Hospital's rule. That means we take derivative of numerator and denominator separately. Limit of x minus sin x upon x cube as x tends to 0 equal to limit x tends to 0, we take derivative of numerator, that is derivative of x is 1 minus derivative of sin x is cos x divided by derivative of x cube is 3x squared. We substitute x equal to 0 in the numerator and denominator, so that we get 1 minus cos of 0 is 1, that is 0, and in denominator 3x square, x is 0, therefore we get 0, so that we get here 0 by 0 form again. That means we, after using L'Hospital's rule, again we get 0 by 0 form, so that we again use L'Hospital's rule. That means we take derivative of numerator and denominator separately, so that we get limit as x tends to 0 of derivative of numerator, that is derivative of 1 is 0, minus derivative of cos x is minus sin x, so that minus minus plus, so that we get sin x, divided by derivative of 3x square is 6x. If we put x equal to 0, then we get sin 0 is 0 and 6 into 0 is 0. So that again here we get 0 by 0 form. So we use L'Hospital's rule again. It means we use here L'Hospital's rule again, since the indeterminate form is 0 by 0. That means we take derivative of numerator and denominator. So that limit of x minus sin x upon x cube as x tends to 0 equal to limit of derivative of sin x is cos x upon derivative of 6 is 6 as x tends to 0. And as x tends to 0, cos of 0 is 1. So that in the numerator we get 1 and in the denominator 6 as it is. So that finally we get the result equal to 1 by 6, which is the limit of given function. Thank you.